Today in this session we will be discussing about longitudinal control. What is the meaning of longitudinal control? Let us again try to understand from our very popular diagram. This is Cm versus Cl, and you know this is the equilibrium point or trim point. Okay, this is the trim point, this is the equilibrium point, that is net force and moments are 0, and you could see from here Cm is 0, this is 0 here as far as Cm is concerned. And what is typically is that one of the examples will be, let's say the airplane is cruising. Okay, so what is happening? Lift equal to weight, thrust equal to drag, and net moment is 0. So cruise is also a trim point, right? And we see that at trim, at equilibrium, the slope dCm by dCl is negative, so it is statically stable. This much we understand, right? Also, if I little bit of stretch further, I see that if by some disturbance, if Cl from here it gets increased to another point, let's say Cl at 2, the Cl has increased, then the airplane being statically stable will automatically generate a negative pitching moment, right? And it will try to reduce the Cl, so it will have initial tendency to come back to the Cl trim. So this is another way of explanation that the airplane is having static stability. Okay, now our problem of control is how to actually fly at a different Cl. We want to fly at different Cl. A physical situation is, suppose I fly at a speed v1 at a Cl1, let's say v1 at a Cl1, and I'm maintaining lift equal to weight. Correct? Let's say that is here Cl1 and flying at the v1 and lift equal to weight. Now I want to fly it at another trim in another cruise condition where v1 is v2 and Cl is Cl2 and Cl2 is greater than Cl1, so naturally v2 will be less than v1 because weight is same, because lift equal to weight I am maintaining at the same altitude. The point is all these things I am doing where altitude is same, right? This you could easily understand. This aircraft is flying at altitude, say density is rho, the v1 and Cl is Cl1. Now at the same altitude the airplane wants to fly at a lower speed v2, so he has to fly with a different Cl, I call it Cl2. Since lift has to be same because weight is same, so Cl2 has to be more than Cl1. So pictorially I want to fly at a trim at to this point, but we know by now the moment I try to take it here, immediately some negative pitching moment will come because it is statically stable. So if I want to really fly at this point to so I have to ensure that this negative moment is nullified by a positive moment. And how can I get that positive moment? Positive moment will come when I put, recall this is the tail, this is the elevator, and CG is somewhere here. So if I want to generate a positive moment, I have to put the elevator up. If elevator is up, force will come downward, which will give me a positive moment. That means I have to deflect the elevator such a manner at Cl2 such that whatever negative moment is generated here, that gets nullified by this positive moment. Correct? So what you have seen, by doing that, if I now is a straight line, I just extend it, I see there is a increase in delta Cm. Because by giving the elevator deflection, the static stability is not going to change, right? Okay? Elevator will not change anything on stability because it's a control thing. Okay? Elevator doesn't decide the stability. It is the total tail, which includes elevator area, which decides the static stability. Since that is same, So this line will be parallel, their slope will be same. Only thing, if I want to fly from 1, I want to step up to 2, I have to generate this much of Cm, delta Cm. And who generates this? Who helps us to generate this? Elevator deflection. So one question would be, how much elevator I have to deflect to get equilibrium at Cl2? That is one of the questions we will have. Okay? So that is basically what we are looking for is longitudinal control. What is the delta E trim required for different Cl trim? That is, if I now want to fly here, then how much delta is required? If I want to fly here, how much delta is required? And final question comes, can I really fly here? Because suppose if I am flying here and if I draw a line like this much of negative moment needs to be nullified by a positive moment generated by elevator deflection. It may happen, you will see that you don't have that much of elevator deflection because elevator, you can deflect it to a certain extent. Beyond that, say 15 to 20 degrees, normal case, the elevator may stall. So we have to be also careful that I need to have appropriate elevator deflection to trim whatever CL I want to fly at. There's a limit of CL because if I go on increasing the angle of attack, it may stall. Also, even if you generate that much of CL by some method, you need to check whether you have got realistic elevator deflection possible or not, because elevator also beyond 15-20 degrees may stall for normal cases, right? So these are the issues we'll be talking about, and we will try to develop a mathematical formulation before we exclusively answer these questions, and we'll be solving a problem to get better insight into what is happening here. Okay, so let us start doing the mathematical formulation for this. This is the elevator. As per the convention, this is delta E positive, delta E or elevator down is positive, and elevator up is negative. This is a matter of convention. Okay. Now, if you see CL is not only function of angle of attack, it is also function of delta E, because as I am changing the elevator deflection, the CL on the tail is changing, so overall CL of the airplane also will change, right? So far we are talking about CL as a function of alpha. Now since the elevator is being deflected, it also becomes function of delta E. Again we assume linearity, and we expand CL as CL equal to CL naught plus CL alpha into alpha plus CL delta E into delta E. We know what is CL naught, but what is CL alpha also we know. It is a partial derivative, that is dCl by d alpha, okay, where delta E is fixed. That is, it's a partial derivative. I am changing one variable at a time. So that is CL alpha. Similarly, CL delta E is dCl by d alpha. Similarly, CL delta E is dCl by d delta E, keeping alpha constant, because these are partial derivatives. Okay. If I want to generate CL alpha in a tunnel, how do? I go inside a tunnel, I mount the model inside the tunnel, and this is the velocity vector. So I can always put this at different orientation and find out what is the lift, and I know what is the angle of attack, so I can find out CL alpha. Similarly, if I want to find CL delta E, then I will not change alpha at all. What I will do, I will take this model, I'll keep this axis, and then I'll give deflection, some delta E, different deflection, and I will measure what is the lift forces coming, and that additional lift force at alpha equal to 0 is attributed to delta E. So from there I find out what is CL delta E, right? So also note one thing here, when I'm writing like this, you are assuming that the airplane is at there are no pitching motion. Airplaning as at equilibrium. All are called, all this modeling is done where no such pitching motion or oscillatory motions are there. It is at an alpha particular delta E elevator deflection. What is the CL it will see? Right? For example, when I actually deflect an elevator, the airplane will take some time, some oscillation, and then go to this steady state condition type, fixed alpha and fixed delta E. So we are only analyzing that final point. We are not talking about the transient. The transient will talk in terms of dynamic stability. Okay? So these are typically like static performance type. Okay? So now let us have a closer look. What is the CL delta E? We are very smart now. We know what is CL alpha. We know what is CL naught. So let us try to understand what is CL delta E. How can I calculate CL delta E? I repeat here that all this formulation what we are doing, you try to understand it, but however the clarity, you become master when you solve some numericals. You will find, oh my God, this is so straightforward thing, right? So have patience and try to follow whatever I am telling. We are trying to see what is CL delta E. See, because of delta E deflection, what is the delta lift on tail? That is equal to half rho v square at tail, S tail into CL tail because of delta E. We're talking about delta E deflection, right? So what is delta L? That will be delta L lift by half rho v square S free stream, right? Because this lift is proportional to the ST, horizontal tail area. But when I non-dimensionalize, I do it not only with free stream but also reference area, which is in general wing area, right? So if I do that, again I get half rho v square at tail, that is dynamic pressure at tail, half rho v square free stream into ST by S. S is from airplane, it is the wing area. So this I can write as neta ST by S CL tail. What is the CL tail? CL tail is change in the lift CL, lift coefficient CL tail because of elevator deflection. How can CL change? CL change if by giving elevator deflection you are changing the angle of attack at the tail. See, one way to visualize this, if it is symmetric like this, the zero lift line is here. That is, at alpha equal to 0, lift is 0. The moment I deflect it by delta E, I am actually introducing a camber, so I can say my zero lift line has some angle, right? So actually, I can say the alpha at the tail is somehow changed because of elevator deflection, right? Aerodynamist will say the circulation around that horizontal tail has changed, so there will be change in the lift. Okay, so this I can again write delta L equal to neta ST by S and dCL T by d delta E into delta E. What is the meaning of this? As I was explaining, the CLT is because of change in delta E. So I want to know how much CL tail changes with delta E. If I know this gradient, I multiply with d delta E to get CLT. So I have written delta L like that. Now, let us carefully see. d CLT by d delta E could be written as d CLT by d alpha t into d alpha t by d delta E. Do you see now what is happening? What is dCLT by d alpha t? What is this? dCL by d alpha of tail. This is CL alpha tail. And this d alpha t by d delta E, physically what does it imply? It implies per unit change in elevator deflection, how much alpha tail effectively is being changed. Okay, that causes the additional lift. And this is a parameter tau. So I can write this as dCLT by d delta E, CL alpha t into tau. And this tau I can, in textbook you see this tau is called flap effectiveness parameter. And typically this you can get through some empirical graph. If you see, most of the textbook will give you this variation is something goes like this, and this is typically 0.8, and somewhere here it is around 0.5. And what is this? AC by ST. I'll explain you what is AC by ST, and this is tau. Is the diagram clear to you? Typical variation. So you can see Nelson book, you will find out this graph. This could be 0.4. So typically you are finding that tau value also will be, for this sort of a 0.4 of AC by ST, the value may be around 0.5, 0.6, typical numbers, right? And these are easily, you can find it out by using this graph. We want to know about AC by ST, where AC will be the elevator area. Typically it is from the hinge line, or even for all approximation is the elevator area you take. Okay, this is, and horizontal tail area is ST, is the complete of this. Typically AC is taken from the hinge line, but for all these studies we take AC is the elevator area only. Let's forget about hinge line. I don't want to confuse you because there are no floating tendencies. We have not discussed anything floating tendencies. So let's converge. The AC is the elevator area, and ST is the tail area. Right? If we know this ratio, by using this graph, you can find tau. Typical value of tau will be around 0.4 to 0.5. Tau will be around 0.4 to 0.5. Okay, so what is interestingly we have understood that dCLT by d delta E can be computed through the geometry of the tail. Geometry will tell you what is CL alpha tail, depending upon airfoil. Tau will tell you what is the ratio AC by ST. That is what you should appreciate. Okay. So again, going back to delta CL was given as ST by S neta into CLT, which is typically is delta CLT, if I am more appropriate and more correct. In the last equation I might have written CLT, but you understand that this is a change in additional CL you are getting because of delta E. Okay, so this I can write now as ST by S neta for this, which is here, it will come as CL alpha T into tau into delta E. Let me repeat this. This delta CLT is what? This delta CLT, which is increment in lift because of delta E, will be dCLT by d delta E into delta E. And what is dCLT by d delta E? It is nothing but CL alpha tail into tau. So I have put them here to get delta CL equal to this. Clear? Okay. So now from this I can write CL delta E is equal to ST by S neta CL alpha tail into tau. I just divided this by delta E, so you'll get this expression. So now you know how to calculate CL delta E. Once the geometry of the tail is given, because tail area you know, tail wing reference area you know, neta you know, CL alpha tail you know, and tau also you know. Neta will be typically 1, around 1. For this case, you can take 1 also. Neta, you know, as usual, it is more than 1 if some jet exhausts are blown into the tail, or sometime it will be less than 1. But typically it is values around 1.9 to 1.05, something like that. Okay. But this is clear. you know what is CL delta E. Okay? So what is the meaning of CL delta E? What is the change in the CL because of elevator deflection delta E? What is the sign of this? You see, CL delta E, if I want to know the sign, I know if I am putting the delta E positive is like this, delta is positive. So what type of lift it is giving? It is giving lift upwards, CL positive. So CL delta is actually greater than 0. Sign of CL delta is positive. Okay, clear? Let's do now what is CM delta E. Again, you see, if this is the CG of the airplane, and here this is the tail, and the elevator is deflected like this, this is giving CL, additional CL, which will give a pitching moment nose down. So this positive delta CL because of positive delta E will give what type of moment? Positive or negative? How do I check it? What is the sign of pitching moment? Nose down is negative, nose up is positive. So this is giving what type of moment? About CG, nose down. So whatever moment is coming, delta CM, because of delta CL, right, it is giving negative pitching moment. Okay, this is clear as far as sign convention is concerned. So let us find out what is delta CM by delta delta E, that is per unit change in elevator deflection, how much pitching moment is being generated. Remember, why that is important? Because we have seen, if I go back to CM versus CL, if I was flying here, if you want to fly here, then it is equivalent saying that I need to generate this much of delta CM. So who generates this delta CM? It is through the elevator. What is the mechanism? Elevator, if you deflect it down, it gives delta CL, then it gives pitching moment. In this case, it's negative. If you want to increase to positive, then you have to do other way. Like here, I want to increase CM, right? So I have to ensure that elevator is up so that this force is down, and that gives you nose of pitching moment. Okay? But in a nutshell, this delta CM is caused because of delta E, which gives delta CL. From delta CL, I get delta CM. So let us see the expression for CM delta E, which is delta CM by delta E. So we are looking for an expression for CM delta E. CM delta E, we have already finished. The expression for CL delta E is done. We now understand, we also understand its sign is positive. We are now looking for CM delta E. Who will cause CM? It comes through elevator deflection. Elevator deflection gives CL, and CL is the force, and moment about the CG will give CM. So that will be equivalent saying CM per unit delta E. So I want to now formulate for delta CM. I know CL delta is neta ST by S CL alpha tail into tau. So delta CM, because of this CL delta E, which is coming because of elevator deflection, that will be ST by S, neta will be here. Now CL alpha T the tau into delta E, because this is CL delta E. So what is the CL because of delta E? CL delta E into delta E. So this is portion is CL delta E into delta E. So this is the CL. Okay. Now it will give a moment. So let me write, this is delta CL because of elevator deflection. So moment means it has to be multiplied with moment term LT. What is LT? You know, if this is the CG and if this is the tail, horizontal tail, if this is the AC, so this distance is LT. It is called tail moment arm, okay, for horizontal tail. So if I write like this, do you think I am correct or am something I am missing? When I am writing delta CM, please understand, I need to write a non-dimensional. So this is non-dimensional with C bar. Okay? This should be very, very careful about it. because I am talking about non-dimensional delta Cm, so LT by C bar. But still, this is not correct. There is something wrong in this. What is wrong in this? Could you see? Remember, when writing moment and all, we are also bothered about the sign. Please see here. If delta is positive like this, what sort of force it will generate? This is the elevator. Delta is positive by convention. So that will give force in this direction, delta CL as a non-dimensional quantity. That will give what type of moment? Will give nose down pitching moment. So I have to put minus sign here. Clear? Just to take care of the sign convention. So now if you see, delta Cm is equal to minus neta into St by S into LT by C into CL alpha T into tau into delta E. So Cm delta E, which is delta Cm per unit delta E. If things are linear, so I can easily use this. This is equal to minus neta St by S LT by C CL alpha T into tau, which I can write as minus neta VH into CL alpha tail into tau. This is Cm delta E. What is VH? By now you know VH is tail volume ratio, right? VH is tail volume ratio STLT by SC bar. Do you see one interesting here? The interesting thing here is, if I want to increase the control power, this is also called, for information, elevator control power. Okay? You can very obvious, because if Cm delta is strong, it will give a large moment for a smaller elevator deflection, and you can easily pull up or pitch up or pitch down the airplane. But if you see here, I can increase Cm delta E by increasing the VH value, that is tail volume ratio. Meaning thereby, if I want to increase Cm delta E, then I have option like I increase tail area, I increase tail moment arm, I increase both of them, or in a combination. So this tail volume ratio is extremely important parameter which is evolving through our discussion. And that's why I told you, if VH I can take initial value during design from 0.5 to 1.0 even, but you are very clear, if you are taken 1.0, the Cm delta E value will be very high. So we have now understood what is CL delta E, what is Cm delta E, and it goes without saying, from the expression and from the understanding, you are very well clear the sign of Cm delta E is negative, right? Physically also, you know, if I deflect the elevator down, which is positive, and CG is here, it produces a lift like this, which gives me a nose down moment, which is negative. So sign of Cm delta E is less than 0, and sign of Cl delta, we have already checked, it is greater than 0. Okay. Typical value of Cm delta E for lightweight aircraft will be from minus 0.8 to minus 1.5. Cl delta E could be 0.5 to 0.7. Around this type of range you will get it, right?